In the last lecture, so we discussed about what is the normal subgroups and its properties. So what is the definition of normal subgroup? And we take a theorem: a subgroup H of a group G is normal if and only if G H G inverse is equal to H set itself. So this is the theorem we taking here. So also we take another theorem: a subgroup H of a group G is normal if and only if every right coset of H is equal to the left coset of H. And also we discuss some results related to normal subgroups. So every subgroup of an abelian group is a normal subgroup. So we take a definition in this lecture. So what is the definition? If H and K be two subgroups of a group G, we defined set HK. H is a subgroup and K is also subgroup of G. Then HK is what? HK is equal to the set of all such small hk where h small h belongs to capital H and small k belongs to capital K. So this is a very simple definition. So where it is necessary, note that the HK is non-empty subset of G here. So this is a very simple definition. So what is the theorem? If HK is a subgroup of G, if and only if HK is a subgroup of G, if and only if HK is equal to KH. So that is proving here. Okay. So theorem is very simple. So what is the proof of this theorem? Let HK be a subgroup of G. Okay. Let HK be a subgroup of G, that is given here. So first part of proof. So if part here. So then prove that. HK is equal to KH. So let us take HK be a subgroup of G here. So then let X is an element of HK. Okay. If X is an element of HK, implies that X inverse is also element of HK. Since HK is a subgroup of G. Okay. HK is also group. Then by property inverse element exists also. So if X belongs to HK, so this implies that what? So X inverse also belongs to HK because since HK is a subgroup, HK is a group. So HK is a subgroup of G. So what is X inverse? X inverse is equal to some HK. X inverse is equal to some HK. So we denote here H inverse is equal to HK for some H belongs to capital H and small k belongs to capital K. Okay. So this implies that. So this implies that what? Taking inverse of both sides. So that is X inverse is X inverse, its inverse is X itself is equal to HK inverse. Then HK inverse is equal to what? K inverse into H inverse. K inverse into H inverse. And if K small k belongs to capital K, then K inverse belongs to capital H, H inverse belongs to capital H. So K inverse, H inverse belongs to KH. K is a subgroup, H is also subgroup of a G. So therefore, this implies that X belongs to KH. X belongs to KH. So this implies that. So this implies that what? X belongs to HK. Since X belongs to KH, this implies that X belongs to HK. So therefore, KH is a subset of HK. So KH is a X belongs to KH implies that X belongs to HK. So this implies that KH belongs to HK. So this is equation 1. Similarly, we prove HK belongs to HK is a subset of KH. As we prove this result, let us see here. So similarly, we can prove HK is a subset of KH from 1 and 2. From 1 and 2, what happened here? From 1 and 2, HK is equal to KH. So, if part is proved here. Let HK be a subgroup of G, then prove that HK is equal to KH, and that is proving here. So this is the if part here, okay? Then what is the only part? So conversely means only part here. So let HK is equal to KH is given. Let HK is equal to KH is given. Let HK is equal to KH. Then prove that HK is a subgroup of G. Then prove that HK is a subgroup of G. So it is a better way to prove something. H is a set, and A, B are the element of H. H is a set in a set. A, B are the element of H. And if we prove A, B inverse belongs to H, A and B are the elements of H, and if we prove A, B inverse belongs to H, then we directly say that H is a group. H is a group here. Okay. So similarly, so this is we already studied that if A, B are the elements of G, then A, B inverse is the element of G, then G is a group. So that is proving here already. Okay. So conversely, let HK is equal to KH to prove that HK is a subgroup of G. So HK is so now this is a proving here. Means AB inverse. So we prove that here AB inverse belongs to HK. So that is proving here. If we prove this, AB inverse belongs to, so A is element of HK, B is element of HK, and if AB inverse is an element of HK, then HK is a subgroup. So that is a very simple definition. Okay. So let AB belongs to HK. A and B are the elements of HK. So implies that implies that A is equal to H1 K1. A is equal to H1 K1. So we write A is equal to H1 K1 and B is equal to H2 K2, where H1 H2 are the elements of H and K1 K2 are the elements of K. So what is AB inverse? So then AB inverse is equal to A is what here? HK. What is B? B is K2 H2 K2 inverse. So that is H1 K1. H1 K1 as it is. So inverse of this is H2 K2 inverse is what? K2 inverse into H2 inverse. H2 inverse. Okay. So then H1 K1 K2. So we use the properties of commutativity, associativity, existence of inverse, existence of identity. By using this property, we are not discussing in detail. So just we write directly here. So what happened here? So this is H1. So K1 into K2 inverse and H2 inverse. Okay. By using associativity property here. Okay. So AB inverse is this. So this is AB inverse. AB inverse is equal to H1 into K1 K2 inverse into H2 inverse. Okay. So now we take this part only. This. We take K1 K2 inverse into H2. Okay. So K1 K2 inverse into H2. So this is belongs to KH. Why? Because this is belongs to K. K is a subgroup. K is a subgroup. So K1 K2 inverse. So K is a subgroup. So that is K1 K2 K inverse into H2 inverse. So H2 inverse belongs to H. So K1 K2 inverse belongs to K. So this is belongs to KH. But what is KH? KH is what? HK. So this is HK. Okay. So HK. So therefore this element can be written as K1 K2 inverse is equal to H2 inverse. So this is H belongs to H. K belongs to K. So this can be written like that. HK for some H belongs to capital H. K belongs to capital K. Okay. Then AB inverse is equal to. So what is AB inverse? So what is the AB inverse? So AB inverse is this. AB inverse is this. Okay. This is very simple. So H1 as it is. H1 as it is. What is this? So what is this? This is HK. So this is HK written here. So H1 into HK. Okay. So what happened here? So this can be written as H1 into H into K. H1 into H into K. But H1 into H belongs to H. No doubt. Closure property. H1 into H belongs to H. K belongs to K. So this implies that what? So that is AB inverse belongs to HK. So AB inverse belongs to HK. So AB inverse belongs to HK. So by definition, so very simple. So this implies that HK is a subgroup of G. So this is a converse part of the theorem. So HK is a subgroup of G. So if we taken here HK is equal to KH, then we prove that HK is a subgroup of G. So therefore, HK is a subgroup of G if and only if HK is equal to KH. So this is a theorem, and we taken here theorem. So theorem. So then there are so many theorems regarding the multiplication of two subgroups. Okay. So now we take one more important definition. What is the center of a group? What is the center of a group? What is center of a group? Definition is very simple. Center of a group. Okay. So definition. Let G be a group. Let G be a group. Let ZG. So this is a notation of the center of a group. So what is the center of a group? So ZG is a simply notation. So this is defined as it is a set of all such X belongs to G, where XG is equal to GX for all G belongs to G. Okay, belongs to G is called center of a group. Center of a group. So this is a very simple definition. So what is the definition? Let G be a group. Then ZG. So this is a set of all such X belongs to such elements X, where Xg is equal to Gx for all G belongs to G. So Xg is equal to Gx. Then such X and those set, that set, so that is ZG is called a center of a group G. So we take a theorem. So there is a very simple theorem, and proof is also very simple. So the center ZG, the center ZG of a group is a normal subgroup. Of G. Okay, so proof. So G is a group. So ZG is also set. So ZG is the center of ZG of a group G is a normal subgroup. So prove that this group ZG group is a normal subgroup. So what is the definition of a normal subgroup? So just we write here. So what is a normal subgroup? So if G is a group, then the group is said to be normal subgroup. Then what happen here? So that is GX. G inverse belongs to G. if G X G inverse belongs to G, then the group G is said to be a normal subgroup. So just we proving here. So what is proving here? So that is ZG. So what is ZG? So this is the center of a group. So if GXG inverse belongs to ZG, then the ZG means center of a group is a normal subgroup. So that is the definition of a normal subgroup here. Just we revise. Okay. Let G be a group. So we have again we write. So definition, what is ZG? So what is the definition ZG? So that is X belongs to G. So we repeat here. So that is where XG is equal to GX for all G belongs to G here. Okay. So this is the definition of center of a group. So what is it to prove that? Prove that. So what is proving? So ZG is a normal subgroup. Normal subgroup. ZG is a normal subgroup of G. Let X1 and X2 be the elements of G, two elements of G. So we consider that. So that is the elements of ZG. Okay, so ZG. Then by this definition, what happened here? So then X1G, by using this definition, X1G is equal to GX1 and X2G, because X2 is the element of this center of a group. So by using this definition is equal to GX2. GX2 for all G belongs to G here. G belongs to G here. Okay. So this implies that. So this implies that. So we take here. So this part. So that is we have X2G is equal to GX2. So pre-multiplying this by X2 inverse, X2G, again pre-multiplying this X2 inverse. So is equal to multiplying this X2 inverse GX2 into X2 inverse. Okay, then what happens? So this implies that. Okay, so this implies that. So multiplying X2 inverse to left and right, to this left hand side and right hand side. So we get this here. Okay. So what happened here? So that is X2 inverse into X2. So this can be X2 inverse into X2 is the identity element. So that is E into G, again G. So that is G X2 inverse. G X2 inverse is equal to. So what is X2 into X2 inverse? X2 into X2 is the element, its inverse and its multiplication. So that is identity element. So G into identity element is G itself. So that is X2 inverse G. So this implies that. So what happened here? So this is also definition. If Xg is equal to Gx, then X is an element of center of G. Therefore, similarly, what happened here? X2 inverse is the element of center of G, ZG. So now X1, X2 inverse into G is equal to what happened here? So that is X1 by associative property X2 inverse into G. X2 inverse into G. So this equal to. So what happened here? This equal to X1 G commutative property X2 inverse. This can be done as. So that is what happened? So this equal to X1G associativity X1G into X2 inverse. So this equal to. So this is very simple here. So this equal to. So this implies that here what happened? So that is X1 X2 inverse into G. So this can be written as x1G into x2 inverse. So this is Gx1. So this is Gx1 into x2 inverse. So then what happened here? So this is equal to, so you write this by using properties, commutativity, associativity, closure, something is there. So this what happened here? So G into x1, x2 inverse. So this write out this here. So x1, x2 inverse into G is equal to this. Again using this definition, center of group. Again using this, if xg is equal to gx for all g belongs to the G, then x is an element of this center of group G. X is an element of this. So similarly, what happened here? So this implies that therefore x1, x2 inverse is an element of Zg. Zg for all x1, x2, for all x1, x2 belongs to Zg. Okay? So what it implies? So therefore this implies that by definition of subgroup, okay, therefore Zg is a subgroup of G. Is a subgroup of G. Okay. So Zg is a subgroup of Z. So what is the next part? So we prove here Zg, so that is center of a group, is a subgroup of G. This is the first, we prove here first part. So what is the next part? Prove that this is a normal subgroup. Prove that Z of G is a normal subgroup. Means prove that Gx G inverse belongs to Zg. Then Z of G is a normal subgroup. So now we prove that. Next part. So what is the next part? To prove that. What happened here? Zg is a normal subgroup. Okay? So that is proving here. First we prove Zg is a subgroup. Then we shall prove that Zg is a normal subgroup of G. Let G belongs to G. Let G belongs to G and X is an element of center of a group Zg. Okay? Therefore, thus Gx G inverse. So Gx G inverse is equal to what happened here? So that is, this can be written as Gx into G inverse. Gx into G inverse. So this can be written as again. So this can be written as x Gx is equal to xg into G inverse. G inverse. So this is also can be written like that, x into G inverse. X into G inverse. So what is this? So this is x. Because G into G inverse is identity element. So x into identity element is x itself. But x is what? X belongs to Zg. So what is this? This is equal to this. So Gx, G inverse belongs to Zg. Therefore, by definition of a normal subgroup, so we prove that here Zg is a normal subgroup. So proof is very simple. So it is necessary to remember all definitions and theorems and some remarks. Then it is very easy to prove any theorem in a group theory. Okay, group theory is very simple. But you remember, you know every definition, every remarks, every notes, and some theorems. So it is easy to understood the group theory here. Okay. So what is the normalizer of an element. What is the normalizer of an element? Same definition as the center of a group. So what is the normalizer of an element? So what is the next part? Normalizer of an element. So we just study what is the center of a group. It is a set of all such elements x belongs to G where xg is equal to gx. So this is center of group. But what is the normalizer of an element here? So definition, let G be a group, let G be a group and A, E, B, A, be any element, A be any element, then the subset of G, then the subset NA. So ZG also subset. So the center of G is what here, and what is the normalizer of an element A? Element A. So is equal to the subset NA is equal to it is a set of such X belongs to G. The set of all elements X belongs to G where XA is equal to AX for all, just what happened here, not necessary for all. So you just find out the normalizer of an element A. Okay. So what is the difference between the definition of center of G and a normalizer of an element only? Just here, normalizer of an element only A. So in the center of G, what is the center of G? So that is Z of G. It is a set of all such X belongs to G. Xg is equal to Gx. For all G belongs to G. For all G belongs to G, capital G. Okay. So this is the normalizer. So this is the normalizer of an element. Okay. So what is the or centralizer of an element A? So what is the theorem? Here, okay. The center ZG, the center ZG of a group G is a normal subgroup of normalizer of an element. Okay, so what is the proof here? So what is the theorem? The center ZG of a group G is a normal subgroup. So this is the normal subgroup of any. So that is the proving here. So proof. Let ZG is the center of group. What is the definition? It is a set of all such X are the elements of G where Xg is equal to Gx, where for all G belongs to Gn. So this is the definition of the center of a group here. So what is, again repeat here, what is the definition of normalizer of A? So this is a set. So identify the definitions of center of a group and normalizer of an element A. So this is a set of all X belongs to G. So this is XA is equal to AX. Okay. So these are the definitions here given. To prove that ZG means center of a group G is a normal subgroup. Is a normal subgroup of NA. Okay, so that is of NA. Clearly, ZG, those two groups, subgroups, those two sets, ZG and NA, these are the sets. And clearly, ZG is a subgroup of G and NA is also subgroup of G. Clearly, ZG and NA are subgroups of a group G. Are subgroups, no doubt, subgroups of G. Okay, so let X belongs to, X is an element of ZG. So this implies that what happened? If X is element of ZG, then by definition of center of a group, so this implies that Xg is equal to Gx for all G belongs to Gr. G belongs to Gr. So if we put G is equal to A, so that is Xa. We take a particular element. So G is A. So we find here normalizer of A. So A is a particular element. So put G is equal to A. So this is Ax. X. Okay. Where A belongs to Gr. Okay. A belongs to Gr. So this implies that what happened? So this implies that X belongs to NA. By definition of X belongs to NA. By definition of normalizer of an element A. So therefore, what happened? So that is, therefore ZG is, so this is a subgroup of NA. So therefore ZG is a subgroup of NA. Means then, so what is the previous theorem? What is the previous theorem? If ZG is a normal subgroup, prove that there. Center of a group, ZG is a normal subgroup. So by theorem, previous theorem, by theorem, so we prove that ZG, the center of G is a normal subgroup. By theorem, so ZG is a normal subgroup. By theorem, so ZG center of a group G is a normal subgroup, and this is a subgroup of NA. But ZG is a normal subgroup, and which is a subgroup, normal subgroup of NA. Okay, of NA. Okay, so by using previous theorem, so proof is very simple here. So we prove this theorem, the center ZG of a group G is a normal subgroup of a normalizer of an element. Okay, so you remember the definition of a center of G and